6-6, systems of linear inequalities. So our objectives for this section is to solve systems of linear inequalities by graphing and to model real-world situations using systems of linear inequalities. Our essential understanding is that you can graph the solutions of a system of linear inequalities in the coordinate plane. The graph of the system is the region where the graphs of the individual inequalities overlap. Okay, so like we saw previously in the chapter with a system of equalities, we used to solve those. We could use graphing, we could use substitution, we could use elimination. Okay? A system of linear inequalities is just the same thing as a system made up of two or more, can have as many as you want, linear inequalities. A solution of a system of linear inequalities is an ordered pair that makes all the inequalities in the system true. And the solution, there doesn't just have to be one solution. So when we were solving a system of equations, right, we were looking for the point where these two lines cross. However, with inequalities, like we saw last time, we shade in a region, so we're now looking for the place where the two regions intersect. So there may be more than one point of that makes the solution, that makes the inequalities true. So anything in this shaded region here would be a solution to the system. Okay, so that's what the last sentence says. The graph of the system of linear inequalities is the set of all points that represent all of the solutions in the system. Okay, so what is the graph of the system? Okay, so we're going to find the solution by graphing. All right, so let's start by graphing the first equation. Y is less than 2x minus 3. And all I'm going to do is graph this equation using a dotted line instead of a solid line, and then shade in the correct region. So 2x minus 3, my intercept is 3, and my slope, my slope is going to be 2. Up 1, right 1, up 2, right 1, up 2, right 1, up 2, right 1, and we're going to make a nice dotted line. Okay? Now, let's fill in the region, and I'm going to use my fill tool on here, which means I have to make a region that I can fill in. We'll come back and we'll fix this later. Let's fill it in with a red color. Let's graph the other one and then we'll clean up my picture. Okay, but before I graph the second equation, 2x plus y is greater than 2, I do want to clean this up so that y is by itself. Okay, now I can graph this very simply. My intercept is 2. My slope is down 2, right 1. Okay, down 2, right 1, or up 2, left 1. And again, I'm going to use a dotted line because it says less than, or sorry, greater than, not greater than or equal to. And to use my fill tool again, I'm going to have to define the region. I'm going to shade above the line because it says greater than, just like we filled below the line before because it was a less than. And let me just map out my region like this. And I'll clean up the border in a second. Let's fill it yellow. And you can see, let's clean this up. And you can see that the place where these two inequalities intersect, I'm just going to make these lines real quick. There's the dotted lines. The region where they intercept is the orange region. So everything in the orange region right there is a part of my solution, is a solution to this system of inequalities. Okay, let's do one more. This is you've got a problem. So the graph of the system, negative x plus y is greater than or equal to negative x plus 5. Start at 5, and my slope is negative 1. I'm going to draw the line. This one's a little bit easier to draw the region. I want to shade above it because it says greater than or equal to, and I have a nice solid line because it says or equal to. Ooh, not perfect, but it's okay. Let's fill that red. And now let's graph the second line, but before I do, let's just add 3x to both sides. So y is less than or equal to 3x minus 4. Intercept. And the slope is up 3, right 1. 1, 2, 3, right 1. And we make a nice solid line because it says less than or equal to. And again, I'm going to shade now below the line because it says less than. So let's define out my region so I can use my filling tool. I wish I didn't have to draw this twice like this, but that's the way this tool works. And we have our orange region that is the solution to this system of equations. Okay? So unlike when we have a system of equalities, there's not just one right answer. Okay? Any point, right? This point, this point, this point, this point, any of these points inside this orange region are solutions to this system. Okay. We can combine your knowledge of linear equations with your knowledge of inequalities to a graph using a system of inequalities. So let's look at a picture and write a system of inequalities from the graph. So what system of inequalities is represented by the graph below? So we have the blue boundary line right here, and it looks like it's shaded this way. We have the red boundary line right there. It's shaded below it. And where the blue and the yellow come together, this is my solution, the green area. Okay, so let's write an equation for that. The blue line is a solid line. It has an intercept at negative 1, and it has a slope of 1. So that line looks like y is going to be greater than or equal to, because I'm shading above the line, right, above the line, and the slope is 1. So x minus 1. Whereas the red line, the dotted line, is 2, 3, 4, 5, so that's a 5. Y is going to be less than, because I'm going to shade below the line, and the slope here is down 1, right 2. So negative 1/2 x plus 5. And there is my equation of this region of this system. Okay, let's try a got it problem. One more. Okay. So again, I'm going to shade below the red line and below the blue line as well, right, to get this region right here. So below the blue line to make the blue, below the red line to make the yellow, the green is where they overlap. Nice, they both have the same intercept. So start with the blue line. The slope of the blue line is up 1, right 2. So that's y. I'm going to use less than or equal to because it is solid. The slope is 2, and the intercept is 1. For the red dotted line, that's y, less than because it's dotted, and the slope here is down 1, right 2. So that's negative 2x plus 1. And there's my system. In part A is the point where the boundary lines intersect a solution of the system. So let's look back here. Is this a solution of the system? Well, it's a solution on the blue line, but not on this one because it says y has to be less than negative 1/2 x plus 5. That point would be where it would be equal to negative 1/2 x plus 5. So in this case, it is not a solution to the system. You can model many real-world situations by writing and graphing systems of linear inequalities. Some real-world situations involve 3 or more restrictions, so you must write a system of at least 3 inequalities, which is normal. Let's look at this word problem. You are planning what to do after school. You can spend at most 6 hours daily playing basketball and doing homework. You want to spend less than 2 hours playing basketball. You must spend at least an hour and a half on your homework so you can pass all your classes. What is the graph showing how you can spend your time? So let's get a little bit of room here. Let's keep the question right there. Notice how I only included the positive numbers on the graph, which is normal, because how do you spend negative hours doing homework? That doesn't make any sense. Okay, so let's define our variables. X is going to be time playing basketball. Y, let's call time on homework. All right, so the first sentence says, let's get the first. You are planning what to do. You can spend at most 6 hours playing basketball and doing homework. So that means that no matter what you do, that has to be less than 6 or equal to 6. Okay? Right? So the time you play basketball, the time you spend homework has to be less than 6 because the most time you can spend is 6. So it has to be less than that. Next, you want to spend less than 2 hours playing basketball. So X has to be less than 2. You must spend at least an hour and a half on your homework. So Y has to be greater than or equal to 1.5, okay, but I'm going to write it as 3 over 2, 1.5, okay? Or actually, let's just put it as 1.5. Okay, so let's graph this system. That's going to be our dotted line. These two are going to be our solid lines, and then we'll see what region intersects. So let's start with x plus y is less than or equal to 6, which I can rewrite if I subtract x from both sides. Right? If I have x plus y is less than or equal to 6, subtract x, we have y is less than or equal to negative x plus 6. So that means it starts there at 6, and my slope is a negative 1. Okay? Let's try to keep these lines kind of straight. Okay. So there's my first constraint. Okay. Next, x is less than 2. So that's going to be a vertical line, and we're going to use a dotted line. And finally, y is greater than or equal to 1.5. Okay, so that's going to be right there, and we'll put a nice straight boot. Okay, so for this one, we're going to shade below. For x, we're going to shade to the left, and for y, we're going to shade above. So this is the region right here. So any amount of time in that little region right there will fill all these different constraints. Okay. For our got it problem, kind of big numbers here, so this is going to be kind of hard to draw a picture. So let's set it up, and then I'll graph it using a graphing calculator. So you want to build a fence for a rectangular dog run. Okay, so rectangular means that we're going to make some sort of thing like this so that the dogs can run around. You want the run to be at least 10 feet wide, so let's call the length x is going to be the width, and y is going to be the length. So we want x to be at least, so that means that it's going to be greater than or equal to 10. Y can be at most 50 feet long, so we want that one to be less than 50. And we have 126 feet of fence. That means in order to build this rectangle, if this is the length and this is the width, right, we're going to need to build two sides of each. So that means 2x plus 2y has to be less than or equal to 126, or else we would run out of fence. Okay, so like I said, these numbers are kind of big. Uh, so let's use a graphing calculator. I did this on Desmos. Oops. So if you're not familiar, Desmos is a very nice graphing calculator. If I could grab it, there it is, that we can use to graph anything. All right, so we can see here, I have my three constraints set up on the left, and we can see that this area right in here, is where the three graphs or the three different constraints overlap. Okay? So any of those would be solutions to the system. All right, so to graph the system, right graph the two lines, shade above the line here, below the line here, and see where the two things overlap. What system of inequalities is represented by the graph on the right? We can do this one real quick. So there's my intercept for the red line. For the blue line, it would be y is greater than or equal to, the slope is 3. So that's 3x plus 3. And for the red line, we have a slope of negative 1. So y is going to be less than negative x minus 2. So 3 is just like the two word problems that we just set up before. Cherries cost $4 a pound, grapes cost $2.50 a pound. You can spend no more than $15 on fruit, and you need at least 4 pounds of fruit in all. So we have, let's call cherries x, grapes y. We have 4x plus 250y. You can spend no more, so that means I have to spend less than or equal to 15. And I want at least 4 pounds. So there's my system. Okay. How can you determine whether, and then you just solve it with graphing or however you want. How can you determine whether an ordered pair is a solution of a system of linear inequalities? Well, we could always plug it in and see if it makes both of the inequalities true. Suppose you are graphing a system of two linear inequalities and the boundary lines for the two inequalities are parallel. Ooh, this is a good question. Does that mean the system has no solution? So let's think about this. Here's my graph. Let's just make it positive. Here's my two parallel lines. Does that mean this system has no solution? This is what it would mean, that if these were equalities, because these lines never cross, but because the boundaries have to cross, if we're going to talk about something that's less than this line and bigger than this line, it would cross in the middle. Now, if it was greater than this one and less than this one, then the two regions would never cross and it would have no solution. But just because the lines are parallel does not mean the system has no solution. It could have a solution in between the two lines. How is finding the solution of a system of inequalities different than finding the solution of a system of equations? How is it the same? Well, it's different because we're not going to use substitution, we're not going to use elimination, we're just going to graph the system. And that is a way to solve a system of equations, of equalities. So that's how they're the same. We're both going to use the one technique of graphing, but another way that they're different is that the system of inequalities is always going to have infinite number of solutions, every point possible in between the two lines. Whereas a system of equations is either going to have 0, 1, or infinite number of solutions if they're the same line. Okay? And that was 6-6, systems of linear inequality.